Hey everyone, and welcome to The Explainer. Today we're diving into something absolutely fascinating. We're breaking down the complete story of the SHD-CCP project, the scalable hybrid distributed cognitive pipeline, and its massive migration from a clunky monolithic legacy structure to an ultra-efficient, locally executed version 2.0. If you've ever wondered about the sheer engineering willpower it takes to run massive AI pipelines entirely on consumer hardware, you are absolutely gonna love this.
Right, so it all begins with this profound question. How exactly do you liberate a complex AI from the cloud? I mean, for years, the underlying assumption in the industry has been that massive cognitive pipelines require massive centralized cloud servers, right? But what if you could sever those tethers completely? What if you could take all that immense processing power and run it locally, without sacrificing speed? Well, today, we're going to look at the exact technical roadmap of how this project pulled that off. Okay, let's dive into this real quick. Here's our roadmap. First, the path to an efficient AI pipeline. 2. Absolute cloud independence. 3. Optimized memory management and vector calculations. 4. Modern API and pydantic validation. 5. 127 successful unit tests. And finally, 6. The next steps with Rust integration.
All right, kicking things off with Section 1, the path to an efficient AI pipeline.
You know, extracting core components from a highly intertwined legacy framework is, well, it's a massive headache. But just look at the sheer contrast here. On the left, we've got the legacy monolith v4.7.2. This thing was built on traditional, linear transformer parameters, so it was heavy, cumbersome, and just inherently chained to cloud infrastructure. But on the right, that's the new reality, the state-free modular pipeline v2.0. The engineering team ripped out those linear parameters and replaced them with agile, non-linear 3D data point clouds. And instead of loading everything into crazy expensive RAM arrays, this new architecture orchestrates data via low-level page streaming directly from high-speed local SSDs. It's literally a completely different, infinitely more agile beast.
Moving right along to Section 2, absolute cloud independence.
That structural shift brings us to what is arguably the biggest overarching victory of this whole migration, achieving true, absolute cloud independence. Look at these specs. The system is now fully verified to execute locally on standard consumer processors, like an AMD Ryzen, completely untethered from remote servers. And they enforce this through a brilliant fail-closed isolation mechanic. By setting a specific environment gate, SHD-CCP_LMSA available to 0, the system guarantees that external context fetchers are strictly lazy and blocked by default. We're talking 0 network sockets opened, 0 background thread pools initiated unless you intentionally ask for them. It's uncompromising local privacy. Your data literally never leaves your machine.
Which brings us nicely to Section 3, optimized memory management and vector calculations.
So, you might be wondering, how on earth is it possible to run such a complex system on a standard CPU without it just grinding to a complete halt? Well, it all comes down to a technical optimization called C-contiguous memory allocation. Think of it like packing boxes into a massive warehouse. If you just throw boxes in randomly, wherever there's space, finding and pulling a specific set later takes forever, right? But if you pack them flawlessly, tightly, end-to-end, with 0 gaps, you can grab exactly what you need instantly. By enforcing strict NumPy array formatting across all those high-dimensional token vectors, the system guarantees perfect memory layout stability. This layout completely eliminates fragmentation and enables 0-copy memory borrowing, meaning the CPU doesn't even have to waste time duplicating data just to read it.
And this chart right here brilliantly illustrates the real-world payoff of that perfect warehouse packing. Look at these median encoding latencies running locally on an AMD Ryzen. For a massive 512-dimensional vector operation, the system knocks it out in less than 2.0 milliseconds. And for insanely complex 4096-dimensional operations, it's still finishing in under 10.0 milliseconds. No way, right? It just proves that when you feed consumer CPUs data that is perfectly optimized for their cache lines, they can deliver absolutely blistering AI performance.
But hey, memory speed isn't just about arrays, it's also about how the software physically talks to your hard drive. To handle this, the team built a dynamic cross-platform map layer. On Windows, it cleanly wraps the OS context to sidestep those completely frustrating file-locking EPRM errors. And on Linux, it invokes sequential memory advice MAD, MADV_sequential, to keep disk page thrashing basically at absolute 0. It's so smart because it adapts dynamically, giving your specific operating system exactly what it needs to read that SSD data as fast as the laws of physics allowed.
All right, jump into Section 4, modern API and pydantic validation.
Now that the deep memory layer is sorted, we need to zoom out a bit and look further up the architecture stack. How does this newly liberated system actually communicate and validate its own internal data? Well, they transitioned to a highly modern modular API structure. They ruthlessly stripped out all the legacy clutter, specifically those global mutable singletons that are notorious for causing weird, unpredictable bugs. Instead, they brought in explicit, thread-safe state containment using Fast API's dependency injection. And for data safety, every single piece of network parsing was ported over to Pydantic V2, which creates these ironclad, robust validation contracts. Throw in fully asynchronous server-sent event streaming, and you've got real-time inference routing across different AI experts without any blocking overhead whatsoever.
Let's look at Section 5, 127 successful unit tests.
Because, let's be honest, bold architectural claims are just talk until you actually test them. 127. That is the exact number of rigorous unit and integration tests the engineering team threw at this newly extracted version 2.0 framework. And the results? 127 out of 127 passed flawlessly. The entire test execution window for the complete pipeline wrapped up in a staggering 181.09 seconds.
So the crucial point here is captured in this compliance matrix. This isn't just a pat on the back. It's mathematical proof of their architectural contracts. They verified the local isolation, absolutely zero network lookups. They verified the memory continuity with strict C-order arrays. They even proved out back pressure control under intentional frame flooding workloads, showing that if the system gets totally overwhelmed, the queues just gracefully drop old frames and stay non-blocking. It is a 100% regression-free operation.
Actually, I want to highlight one super specific optimization from this validation phase because it's just so clever. 151,936. During the Quen model substrate integration, the team hit a nasty size mismatch on the simulation boundaries. Their fix? They dynamically expanded the token structures to precisely match the true vocabulary floor of exactly 151,936 tokens. By matching that structural floor, they completely bypassed out-of-bounds matrix errors when loading those fragmented model shards off the SSD. It's exactly this kind of precision engineering that makes running it locally so incredibly stable.
Finally, Section 6, Next Steps, the Rust integration. As mind-blowing as this V2.0 triumph is, it's really just setting the stage. Remember that perfect C-contiguous memory layout we geeked out about earlier? That zero-copy memory borrowing was strategically designed specifically to interface natively with Rust. So the upcoming sprint targets two massive steps. Step 1, shifting the memory page table residency queries natively into a Rust core crate. Step 2, porting all the Python and NumPy cosine similarity matrix operations directly into a lightning-fast Rust embedding router. Once those heavy mathematical operations are handled by Rust, we are going to see unprecedented routing speeds that native Python just simply cannot touch.
I want to wrap up today's explainer by leaving you with this powerful quote right from the architecture report. The migration confirms the viability of running massive architectures locally on consumer CPUs. Think about what a profound paradigm shift this is. We are no longer chained to the cloud for advanced cognitive pipelines. With brilliant memory management, strict validation, and uncompromising isolation, having true, decentralized private AI running right on the desktop sitting in front of you isn't just a theory anymore. It is a reality. So the real question is, what are you going to build now that the processing power is entirely in your own hands? Thanks for hanging out with me today, and I'll catch you in the next one.